Hello, my friend. Welcome. This is a place where science meets rest, where we explore the deepest questions of the universe in a calm, soothing way. If you're new here, know that these stories are meant to help you drift into sleep while your mind travels through the wonders of knowledge. Tonight, we'll journey together into ideas that show us the limits of what we can understand, exploring them slowly, gently, so you can let go of the day and settle into the night. Chapter 1. The Human Quest for Knowledge. From the moment our species first walked upright on the African savannas, curiosity has been one of the defining features of humanity. The earliest humans were not merely creatures reacting to their environment, but beings who began asking silent questions. Where did the fire come from? Why did the stars appear at night and vanish with the dawn? What forces made the rains come and go? These were not yet scientific questions in the modern sense, but they were the seeds of an unending drive toward understanding. This impulse to know would shape not only survival strategies, but the very culture, language, and technologies that allowed Homo sapiens to flourish in a world filled with challenges. Knowledge in its earliest form was pragmatic. For hunter-gatherers, understanding the tracks of animals, the seasonal cycles of plants, and the rhythms of migration could mean the difference between life and death. Yet alongside this practical knowledge was something more. In caves across Europe, Africa, and Asia, we find paintings tens of thousands of years old. They do not serve a strictly utilitarian function. Rather, they suggest reflection and representation, a desire to capture not only what is, but what might be remembered, shared, or interpreted. Symbolic thought was itself a leap in knowledge, the recognition that the world could be represented in signs and stories, and that these signs could be transmitted across generations. As societies grew larger and more complex, so did the systems for storing and transmitting knowledge. Oral traditions preserved myths, genealogies, and cosmologies long before writing was invented. With writing, knowledge took on a permanence that oral memory could not achieve. Clay tablets, hieroglyphs carved in stone, and scrolls of papyrus allowed for the recording of laws, astronomical observations, and mathematical insights. The invention of writing was not simply a convenience. It was a transformation of the human mind's relationship to time. What was known no longer depended solely on the fragile continuity of human memory. Instead, it could survive across generations and even civilizations. This externalization of knowledge laid the groundwork for cumulative learning, where each generation could build on the work of those who came before. Ancient civilizations pursued knowledge with remarkable ambition. In Mesopotamia, Babylonian astronomers carefully tracked the motions of the planets, not only for agricultural and ritual purposes, but also to uncover regularities in the heavens. In Egypt, engineers mastered geometry to design pyramids whose alignment with the stars still inspires awe. In India, philosophers speculated on the nature of consciousness and the infinite. In China, scholars cataloged medicinal herbs and mapped the stars with precision. And in Greece, thinkers like Thales, Pythagoras, and Aristotle began to articulate the idea that the world could be explained not only through myth, but through reason and systematic inquiry. To them, knowledge was not merely practical, it was a pursuit of truth for its own sake. This transition from myth to reason marked a critical turning point. While myths gave meaning, reason sought mechanisms. Where once thunder was the voice of gods, it became understood as natural phenomena. The Greek word for nature, physis, gave rise to physics, the attempt to understand the principles governing all things. Yet it would take centuries for these philosophical inquiries to transform into what we now call science. During the Middle Ages, knowledge was preserved and expanded in monasteries, Islamic libraries, and universities. Scholars such as Alhazen developed systematic methods of observation and experimentation. Ibn Sina's medical encyclopedias and Al-Khwarizmi's algebra laid the foundations for later advances. Knowledge was global long before modern globalization. The scientific revolution of the 16th and 17th centuries brought another profound transformation. Figures like Copernicus, Galileo, Kepler, and Newton demonstrated that the universe operated according to laws that could be described mathematically. This shift was not merely about astronomy or mechanics. It represented the radical idea that nature was intelligible through systematic observation, measurement, and theory. Knowledge became testable, falsifiable, and predictive. The invention of the printing press allowed these discoveries to spread widely, accelerating the accumulation of shared understanding. Science became a collective enterprise rather than the insight of a few isolated thinkers. From that point onward, the quest for knowledge grew inseparable from technology. The telescope extended human sight into the heavens. The microscope revealed hidden worlds within a drop of water. Instruments allowed humans to transcend their biological limits and probe scales vast and minuscule. By the 19th century, Darwin's theory of evolution expanded knowledge to encompass the origins of life itself, while thermodynamics and electromagnetism uncovered principles governing energy and matter. Each discovery opened new questions. What was the age of the earth? What lay beneath the atom? How did the brain give rise to thought? The 20th century transformed the pursuit of knowledge in unprecedented ways. Relativity redefined space and time, while quantum mechanics revealed a probabilistic foundation to matter and energy. Discoveries in genetics illuminated the code of life, while computers offered new ways to simulate and process information. Scientific institutions grew to international scale, with laboratories, telescopes, and particle accelerators requiring collaborations among thousands of scientists. Knowledge was no longer the work of individuals, but of collective networks, global communities devoted to inquiry. Scientific method itself became more self-aware. Francis Bacon emphasized induction. Karl Popper introduced falsifiability as a criterion of science, while Thomas Kuhn described paradigm shifts in which old frameworks are replaced by new ones. Imre Lakatos added the idea of research programs, acknowledging that science is not only a method, but also a culture shaped by institutions, funding, and historical context. These philosophical reflections revealed that knowledge is not static. It evolves through struggle, debate, and the slow correction of errors. Instruments reshaped our relationship to the unknown. Radio telescopes revealed pulsars and cosmic background radiation. Particle accelerators uncovered quarks and new symmetries of matter. Interferometers like LIGO detected gravitational waves, confirming Einstein's predictions a century later. In biology, the invention of X-ray crystallography unveiled the structure of DNA, while modern cryo-electron microscopy maps molecules with atomic precision. Each new tool does more than extend our vision. It reshapes the very questions we can ask. Yet with each advance, humanity became increasingly aware of the limits of knowledge. Instruments revealed cosmic horizons beyond which we cannot see. Quantum mechanics showed us that uncertainty is not simply ignorance, but a fundamental aspect of nature. Complexity theory revealed that even when rules are known, prediction may be impossible. Logic itself, through Gödel's incompleteness theorems, suggested that within any consistent mathematical system, there are truths that cannot be proven. The very structure of knowledge seems to carry its own boundaries. At the same time, the scope of human curiosity has expanded to staggering proportions. We now ask not only how to cure disease or harness energy, but why there is something rather than nothing, whether consciousness can ever be explained, and what the ultimate fate of the universe will be. The questions have grown as immense as the universe itself, and the answers often retreat further as we advance. The quest for knowledge, paradoxically, seems to multiply the unknown as much as it conquers it. Still, the drive to know persists. Neuroscience shows that curiosity activates reward systems in the brain, suggesting that seeking knowledge is not simply a cultural trait but a biological imperative. To learn, to explore, to expand the boundaries of what is understood is as much a part of humanity as breathing or eating. And this drive has carried us from stone tools to spacecraft, from mythologies around firelight to images of galaxies billions of light years away. If we reflect on the arc of history, we see that knowledge has always been provisional. What once seemed certain, the immobility of Earth, the indivisibility of the atom, the predictability of Newtonian mechanics, has been revised, expanded, or overturned. The quest for knowledge is not the pursuit of a final truth, but a continuous refinement of models that approximate reality ever more closely. Each generation inherits not only answers, but also the humility to recognize how much remains unknown. Perhaps the clearest image of this dynamic is the interplay between theory and experiment. Theory provides a framework that guides observation. Experiment tests, refines, or overturns the framework. When Newton proposed universal gravitation, he offered a model that could be tested with the motion of planets and falling apples alike. When Einstein introduced general relativity, the deflection of starlight by the sun offered a decisive test. In the quantum era, theories of the subatomic world called for ever more sophisticated instruments: cloud chambers, bubble chambers, particle colliders. In biology, the discovery of DNA structure was soon linked to experimental tools such as sequencing, microscopy, and genetic engineering. Together, theory and experiment form a self-correcting engine of knowledge. Looking ahead, the terrain of inquiry will continue to expand in step with our tools and concepts. Quantum technologies promise new sensors and communication protocols that will expose subtler features of nature. Space telescopes will peer farther back toward the first luminous objects. Biomedical tools will map brain activity at unprecedented scales, testing hypotheses about cognition and consciousness with finer resolution. None of this guarantees simple answers, but each extension of capacity enlarges the horizon of what it is reasonable to ask. And perhaps that is the essence of being human. We are not simply organisms that adapt to an environment. We are beings that question the environment itself. We wonder not only how to survive, but why there is something to survive in at all. We search for patterns, meaning, and laws, even when those laws remind us of our limitations. To know that we cannot know everything is itself a profound form of knowledge. It situates us humbly within the cosmos, balancing our achievements with our limitations. And perhaps it is in this balance, between the light of understanding and the shadows of mystery, that the human quest for knowledge finds its truest meaning. Chapter 2: The Map and the Territory. When we speak of knowledge, we often imagine it as a window onto reality, a clear view of the world as it truly is. But every act of knowing involves a gap between reality itself and our representation of it. The philosopher Alfred Korzybski captured this gap in a striking phrase: "The map is not the territory." No matter how detailed, precise, or comprehensive, a map can never be the landscape itself. At best, it is a useful abstraction, highlighting certain features while ignoring countless others. The same is true of human knowledge. What we call science, perception, or theory is not the universe itself, but a set of models we construct in order to navigate and make sense of it. Understanding the difference between the map and the territory is crucial if we wish to recognize both the power and the limits of human cognition. The human brain did not evolve to uncover ultimate truth, but to support survival. Our senses provide access to only a narrow range of the physical world. The visible spectrum, for example, spans a tiny fraction of electromagnetic radiation. Bees see ultraviolet patterns on flowers that remain invisible to us. Many snakes can detect infrared signatures of their prey. Migratory birds appear to sense Earth's magnetic field directly. The world is filled with signals and structures we cannot perceive unaided. What we call reality, in its raw form, is far more complex than the slice that reaches our awareness. Even within our limited range, perception is not a passive reception of reality, but an active construction. Neuroscience shows that the brain is constantly filtering, predicting, and filling in gaps. Optical illusions reveal just how easily perception can diverge from physical stimuli. In the famous Miller-Lyer illusion, two lines of equal length appear different depending on the orientation of small arrows at their ends. The brain interprets depth cues based on experience, producing an incorrect map of line length. Such illusions are not errors in a defective system. They are the natural consequences of a brain that evolved to generate rapid, useful approximations rather than precise measurements of external reality. This constructive nature of perception extends beyond vision. Our sense of sound, touch, and even time is mediated by neural processes that compress, smooth, and interpret. We never experience the world as it is in a raw physical sense. Instead, we experience the world as processed by our sensory and cognitive systems. The philosopher Immanuel Kant described this by arguing that we never encounter the noumenon, the thing in itself, but only the phenomenon, the appearance shaped by our faculties of understanding. Modern cognitive science, with its emphasis on predictive processing and neural representation, offers empirical support for this idea. If perception is already a kind of map, then science is a map of maps. Scientific theories do not claim to reproduce reality itself, but to create models that are reliable, testable, and predictive. When Newton described the motion of planets using universal gravitation, he was not claiming that gravity was literally an invisible force pulling objects along lines of attraction. He was offering a mathematical model that successfully captured the regularities of planetary motion. When Einstein replaced Newtonian gravity with the curvature of space-time, he did not invalidate Newton's map, but revealed that it was a limited approximation, accurate at certain scales and speeds, but incomplete at extremes. Each scientific theory is a map that can be remarkably effective while still remaining distinct from the territory it represents. This distinction is crucial when considering scientific realism and instrumentalism, two broad philosophical stances about the nature of scientific knowledge. Realists argue that successful scientific theories are true, or at least approximately true, descriptions of reality. If electrons behave in ways predicted by quantum electrodynamics, then electrons really exist as the theory describes them. Instrumentalists, by contrast, argue that theories are tools for organizing experience and making predictions, without necessarily corresponding to ultimate reality. To them, the question, what really exists, may not even be meaningful. What matters is whether the model works. Both perspectives highlight the fact that our knowledge is always mediated by representation. The choice is between seeing our maps as gradually converging on the true territory or as endlessly useful but never fully faithful sketches. Examples from modern physics illustrate how maps can succeed while diverging dramatically from intuitive conceptions. Quantum mechanics uses mathematical formalisms that yield precise predictions, but the underlying reality remains elusive. Is the wave function a description of physical reality or merely a computational tool for predicting measurement outcomes? In quantum field theory, particles are described not as discrete objects, but as excitations of underlying fields, abstractions that cannot be visualized in everyday terms. Similarly, in cosmology, dark matter and dark energy make up the majority of the universe's content according to our models, yet their nature remains mysterious. These concepts function within maps that yield consistent predictions, but whether they correspond to actual entities in the territory of reality is an open question. The biological sciences also demonstrate this interplay. The double helix structure of DNA, revealed by Watson, Crick, and Franklin, provides a map of how genetic information is stored and replicated. Yet the territory of life is vastly more complex than any single molecular model. Epigenetic modifications, regulatory networks, and environmental interactions shape the functioning of organisms in ways that no single level of mapping can capture. Evolutionary theory provides a broader map, explaining the diversity of life and its adaptation to environments, but even it is an abstraction layered over countless contingent histories of survival and extinction. The map territory distinction extends into mathematics itself. Numbers, equations, and geometric spaces are not physical entities but abstractions created by the human mind. They can correspond strikingly well to physical reality, but the relationship remains one of correspondence rather than identity. The famous unreasonable effectiveness of mathematics, as described by physicist Eugene Wigner, highlights how well mathematical maps describe physical phenomena. Why should the universe be intelligible through symbols on paper? Is this a reflection of deep structures in reality or a projection of human cognitive frameworks onto the world? The answer remains uncertain, underscoring the mystery of why our maps work as well as they do. Technology expands the reach of our maps. Instruments such as telescopes, microscopes, and particle detectors extend our senses into domains we could never access unaided. Yet even these instruments are not neutral windows. They too translate, filter, and represent aspects of the world in ways that are interpretable within our frameworks. An image from the Hubble Space Telescope is not a direct photograph, but a composite of data across different wavelengths, mapped into visible light. A brain scan does not literally show thought, but displays patterns of activity interpreted through statistical models. In every case, there is mediation, processing, and translation. Our maps are built not only from perception, but also from technologies that themselves impose their own forms of abstraction. The recognition that all knowledge is representational does not diminish its value. Maps are indispensable for navigation, planning, and understanding. A city map that omits trees and lampposts is still useful if it accurately shows roads and intersections. Similarly, scientific models are powerful even if they omit or simplify vast aspects of reality. What matters is not completeness, but adequacy for the task at hand. In physics, Newtonian mechanics remains entirely adequate for most engineering purposes, despite being replaced at the frontier by relativity and quantum theory. In biology, Mendelian genetics remains useful for plant breeding, even as molecular biology reveals deeper mechanisms. Each map has its scope, and wisdom lies in knowing both its strengths and its limits. Yet the temptation to confuse the map with the territory is strong. Throughout history, societies have mistaken their models for reality itself. Ptolemaic astronomy, with its complex system of epicycles, became not just a predictive tool, but a vision of how the cosmos really was, until Copernicus and Galileo overturned it. In the 19th century, some scientists believed Newtonian mechanics had nearly completed physics, unaware of the revolutions to come. Even today, there are moments when confidence in existing models risks being mistaken for finality. To remember that the map is not the territory is to maintain intellectual humility, recognizing that every model may one day be surpassed, revised, or discarded. Philosophers of science have explored this humility extensively. Thomas Kuhn emphasized that scientific revolutions involve paradigm shifts, where old maps are replaced with new ones that may be incommensurable with what came before. What was once seen as the territory itself is reinterpreted under a new framework. For Kuhn, science does not march steadily toward truth, but oscillates between periods of stability and upheaval. Others, like Paul Feyerabend, argued that even the rules of method are themselves maps, contingent and revisable. There may be no single universal scientific method, but rather a plurality of approaches, each suited to its domain. This perspective raises profound questions about the nature of reality itself. If every access we have to the world is mediated by maps, perceptual, conceptual, technological, what confidence can we have that we grasp the territory at all? Perhaps reality in its fullness is forever beyond human reach, and our maps are simply adaptive tools that allow us to function. Some philosophers have suggested that what we call reality may be a kind of user interface, evolved to present organisms with actionable simplifications. The neuroscientist Donald Hoffman, for instance, has argued that perception is less like a window and more like a desktop screen. Icons represent underlying processes, but never reveal them directly. If this view holds, then all our maps, no matter how refined, may remain icons, useful but never revealing the true depths of the territory. Despite this sobering possibility, the human quest for knowledge continues to thrive on the power of maps. They guide spacecraft to distant planets, predict the outcomes of medical treatments, and allow us to harness the forces of electricity, magnetism, and nuclear interactions. They illuminate patterns in climate, ecosystems, and economies. Though partial and provisional, these maps empower us to act, to anticipate, and to explore. Their imperfection does not negate their value. It defines the horizon of what remains to be discovered. In the end, the phrase, "the map is not the territory," serves as both a caution and an inspiration. It cautions us not to mistake our theories and perceptions for reality itself, but it also inspires us to keep refining, expanding, and comparing our maps, knowing they can grow ever more useful, precise, and beautiful. The recognition of limits is not a defeat, but an invitation to curiosity. If we cannot know the territory in its entirety, we can still draw ever more intricate maps, aware that each line, each symbol, each equation is a bridge between the human mind and the universe it inhabits. And perhaps it is in that bridging that something uniquely human emerges. To draw a map is not only to navigate, but to imagine. It is to acknowledge both our limitations and our capacity to reach beyond them. The territory may remain hidden in its fullness, But in our maps, we see reflections of ourselves, our questions, our creativity, our desire to understand. The map is not the territory, but it is enough to remind us that we are explorers in a cosmos whose depths remain endlessly inviting. Chapter 3. The smallest scales, quantum uncertainty. When physicists in the early 20th century began to probe the behavior of matter at its most fundamental scales, they uncovered a domain that defied the expectations of classical physics. At macroscopic levels, objects obey predictable rules. A ball thrown through the air follows a calculable trajectory. The planets orbit the sun in ways that can be described centuries in advance. But as experimental tools reached the scale of atoms and their constituents, a new picture emerged. Here, certainty gave way to probabilities, and precision encountered a fundamental barrier. The principle that came to define this new domain is known as the uncertainty principle, and it reshaped not only physics, but also our understanding of what knowledge itself might mean. The uncertainty principle, introduced by Werner Heisenberg in 1927, reveals that certain pairs of physical properties cannot be known with arbitrary precision at the same time. The most famous example is position and momentum. In classical physics, one could in principle measure the exact position of a particle and its exact velocity simultaneously. But Heisenberg showed that quantum mechanics imposes a fundamental limit. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This is not a matter of technological limitation, but a fundamental feature of nature as described by quantum theory. To grasp why this matters, it helps to remember that quantum systems are not like tiny billiard balls bouncing around. They are described by wave functions, mathematical entities that encode the probabilities of finding a particle in different states. A particle does not occupy a definite point until a measurement is made. Instead, it exists as a distribution of possibilities. This wave-like nature is what gives rise to uncertainty. A sharply localized wave, corresponding to precise knowledge of position, necessarily involves a wide spread of momenta. A sharply defined momentum requires a broad spread in position. The uncertainty principle is thus rooted in the wave structure of matter itself. This principle challenged centuries of assumptions about determinism. Since Newton, many had believed the universe to be a vast mechanism, its future states entirely determined by its present conditions. If one knew the position and momentum of every particle, one could in principle calculate the entire future of the universe. Laplace's famous demon embodied this vision of absolute predictability. He imagined an intelligence that, knowing all positions and velocities, could foresee the past and future with perfect clarity. Heisenberg's discovery shattered this dream. At the smallest scales, such total knowledge is not only impractical but fundamentally impossible. Quantum uncertainty is not confined to position and momentum. Similar relationships exist between other complementary properties, such as energy and time, or angular momentum components along different axes. The principle is woven into the very fabric of quantum theory, showing that precision always comes at a trade-off. This does not mean that quantum mechanics is vague or indeterminate in the sense of being sloppy. On the contrary, the uncertainty principle is mathematically precise and experimentally verified. It defines exact limits to what can be known and measured simultaneously. Experiments have repeatedly confirmed these limits. In electron diffraction experiments, particles fired through a slit spread out in wave-like patterns. If one tries to narrow the slit to pinpoint the electron's position more precisely, The resulting diffraction pattern broadens, increasing uncertainty in momentum. At the quantum scale, the act of measuring influences the system in unavoidable ways. Unlike in classical physics, where measurement can in principle be passive, in quantum mechanics the measurement is an active interaction, entangling observer and observed. One of the most profound implications of uncertainty is the probabilistic nature of quantum outcomes. When a radioactive atom decays, quantum mechanics does not predict the exact moment it will happen. Instead, it provides a probability distribution, a half-life that describes the likelihood over time. When an electron is prepared in a superposition of states, the theory cannot tell us which state will be observed in any single trial, only the distribution of outcomes over many trials. This intrinsic randomness has been tested to extraordinary degrees of precision, and the results agree perfectly with quantum predictions. No hidden regularity has yet been uncovered. Still, the meaning of this randomness remains debated. Does the uncertainty principle reflect a deep indeterminacy in nature, or is it simply a statement about the limits of human knowledge? Albert Einstein famously resisted the idea of intrinsic randomness, insisting that God does not play dice. He suspected that quantum mechanics was incomplete and that hidden variables might restore determinism if only we could find them. But subsequent work, most notably John Bell's theorem and the experiments that followed, placed strict limits on such hidden variable theories. Tests of Bell inequalities have shown that no local hidden variables can account for quantum correlations. The uncertainty is not just ignorance, it appears to be an essential feature of reality. Quantum uncertainty also has profound implications for technology. Without it, much of modern electronics would be impossible. The operation of semiconductors, lasers, and magnetic resonance imaging depends on quantum effects that are grounded in the probabilistic framework. Quantum uncertainty also underlies quantum cryptography, where the impossibility of measuring complementary variables simultaneously provides a guarantee of security. In quantum computing, uncertainty and superposition are harnessed to perform calculations that would be infeasible on classical machines. What began as a limit to knowledge has become a resource to be engineered. Beyond practical applications, uncertainty reshapes how we think about knowledge itself. In classical science, measurement was a way of peeling back ignorance to reveal a determinate reality. In the quantum world, measurement is a participation in reality, an act that brings about definite outcomes from a haze of possibilities. The observer cannot be fully separated from the observed. This challenges the very notion of objective knowledge as a mirror of reality. Instead, knowledge becomes relational, contextual, and limited. Different interpretations of quantum mechanics attempt to make sense of this. The Copenhagen interpretation, associated with Niels Bohr, embraces the idea that quantum mechanics does not describe reality itself, but only the outcomes of experiments. For Bohr, the uncertainty principle expresses a complementarity. Different experimental setups reveal different aspects of a system, but no single setup can reveal all aspects at once. Other interpretations, like the many worlds view, argue that uncertainty reflects our position within a branching multiverse, where all outcomes occur but we experience only one branch. Bohmian mechanics posits hidden pilot waves guiding particles, restoring determinism but at the cost of non-locality. Each interpretation offers a different view of what uncertainty means, but none escape its constraints on measurement and prediction. At times, quantum uncertainty has been overstated or misunderstood. It does not mean anything goes or that reality is entirely subjective. The probabilistic framework is extraordinarily precise. For example, quantum electrodynamics predicts the magnetic moment of the electron to many decimal places, and experiments confirm it to the same level of accuracy. The uncertainty principle sets boundaries, but within those boundaries, quantum theory is among the most successful frameworks ever devised. It is not the end of knowledge, but a redefinition of what knowledge entails. The uncertainty principle also connects with the concept of quantum fluctuations, which fill the so-called vacuum with seething activity. Even in the absence of particles, quantum fields exhibit temporary excitations that cannot be pinned down precisely. These fluctuations give rise to measurable effects, such as the Casimir force between closely spaced plates or the Lamb shift in hydrogen energy levels. Uncertainty ensures that emptiness itself is never entirely still. The smallest scales are not voids of nothingness, but arenas of restless potential, constrained yet irreducible. There is also an important connection between uncertainty and the stability of matter. If electrons could sit precisely at the nucleus with zero momentum, atoms would collapse. The uncertainty principle prevents this by ensuring electrons maintain a spread of momentum when localized near the nucleus, giving rise to the stable structures of atoms and molecules. What might seem like a frustrating limit is, in fact, a condition for the very existence of the physical world as we know it. In recent years, experiments have pushed quantum uncertainty into new domains. Ultra-cold atom systems, squeezed states of light, and entangled photons allow physicists to test the principle at remarkable levels of control. Squeezed states, for instance, reduce uncertainty in one variable at the expense of increasing it in its complement, illustrating the trade-offs at the heart of the principle. These experiments not only deepen our understanding of quantum mechanics, but also pave the way for technologies such as quantum-enhanced sensors and clocks. Ultimately, uncertainty forces us to confront the boundary between knowledge and mystery. It tells us that the smallest scales are not accessible with arbitrary precision, no matter how advanced our tools become. There will always be a fuzziness in the details, a probability cloud instead of a sharp line. This is not a reflection of human failure, but of nature's rules. Knowledge is therefore not about uncovering an exact blueprint of reality, but about learning to live within the constraints that the universe imposes. For some, this realization is unsettling. It undermines the dream of complete control and total prediction. But for others, it is a source of wonder. To recognize that the universe has built-in limits is to see that mystery is not a temporary gap in understanding, but an integral part of the cosmos. At the smallest scales, certainty dissolves into possibility, and possibility is woven into the very existence of atoms, molecules, and life itself. Perhaps then, uncertainty is not only a boundary, but also an opening. It reminds us that we do not stand outside the universe, detached and omniscient, but within it, participants in a reality that resists absolute clarity. To know that we cannot know everything is itself a profound form of knowledge, and in the quiet recognition of this fact, we may find both humility and awe that the smallest scales, unreachable in their precision, sustain the vastness of the world we inhabit. Chapter 4. The Largest Scales, Cosmic Horizons. When we turn our gaze outward, from the atoms that compose our bodies to the great expanse of the cosmos, we confront another kind of limit to knowledge. At the smallest scales, quantum mechanics reminds us that precision dissolves into probabilities. At the largest scales, the universe itself places boundaries on what we can see, measure, and even conceptualize. These boundaries are not simply challenges to be overcome with better instruments. They are horizons, points beyond which information cannot reach us, no matter how advanced our technology becomes. In exploring these horizons, we encounter not only the structure of the universe, but also the ultimate edges of human knowledge. The first of these horizons arises from the finite speed of light. Light travels at about 300,000 kilometers per second, the fastest speed known in nature. Though vast by human standards, this speed is finite, and the universe itself has a finite age. For this reason, there is a maximum distance from which light could have reached us since the beginning of cosmic time. That boundary defines what cosmologists call the observable universe. Beyond it, galaxies may exist, stars may burn, and structures may unfold, but their light has not yet, and may never, arrive here. Our knowledge of the cosmos is thus circumscribed by a sphere about 46 billion light-years in radius, centered on Earth. What lies beyond remains hidden, a vast territory forever separated from our map. The observable universe is not static. As the cosmos expands, galaxies move farther apart, and more distant regions slip beyond our reach. The accelerating expansion, driven by what we call dark energy, ensures that many galaxies we can see today will one day fade beyond detection. Their light, stretched by cosmic expansion, will redshift until it disappears. In this way, horizons are not fixed boundaries, but evolving ones. What is visible today may not be visible tomorrow on cosmic timescales. We are, in a sense, living in a special era when the universe is still filled with visible galaxies. Far in the future, cosmic horizons will shrink the observable universe to a lonely cluster of stars, leaving future observers with little evidence of the true cosmic past. Another horizon appears in the context of black holes, those regions of space-time so warped by gravity that nothing, not even light, can escape. The event horizon of a black hole defines a point of no return. Information crossing it is lost to the outside universe, inaccessible in principle. From the perspective of an external observer, nothing inside the horizon can ever be retrieved. For decades, this seems to imply a paradox. If information is lost in black holes, does this violate the fundamental laws of physics? Stephen Hawking's discovery of black hole radiation deepened the puzzle, suggesting that black holes can evaporate, but leaving open the question of what happens to the information they consume. The event horizon is thus not only a physical boundary, but a conceptual one, challenging our understanding of the laws of nature. Horizons also arise in relativity through the concept of the cosmological event horizon. This is distinct from the observable universe. While the observable universe marks the farthest distance we can see today, the cosmological event horizon marks the farthest distance from which light will ever reach us, even in the infinite future. Because the universe's expansion is accelerating, there are regions now visible whose light, emitted today, will never arrive here. They are effectively cut off from causal contact. No signal, no probe, no message can ever bridge the gap. Inhabitants of those distant galaxies will never be able to exchange information with us, and vice versa. Horizons carve the universe into separate regions, each with its own domain of knowability. These cosmic boundaries reshape our ideas about knowledge in profound ways. In principle, we cannot map the entire universe. No matter how advanced our technology, no telescope can peer beyond the surface defined by the cosmic microwave background radiation, the relic light from about 380,000 years after the Big Bang. That radiation forms a screen, the last scattering surface, beyond which the universe is opaque to electromagnetic observation. We can infer earlier events through indirect evidence, such as gravitational waves or particle physics models, but direct observation is cut off. The territory exists, but the map will always be incomplete. Inflationary cosmology deepens this mystery. According to this theory, the universe underwent a period of rapid exponential expansion in its earliest fraction of a second. This expansion would have stretched tiny quantum fluctuations into vast cosmic structures, seeding the galaxies we see today. But inflation also implies that the universe may be vastly larger than the observable region, possibly infinite. If so, our cosmic horizon is like a small bubble in an immeasurable ocean. We can chart our bubble with exquisite detail, but the greater universe beyond may remain forever beyond reach. There is an irony here. The more we learn about cosmology, the more we realize how much lies beyond our grasp. For centuries, humans looked at the night sky and assumed they could see the whole cosmos. Telescopes revealed more stars and galaxies, but still, it seemed that with effort, we might eventually know it all. Modern physics has reversed that intuition. Now we know that the majority of the universe's mass energy is dark matter and dark energy, whose nature remains mysterious. We know that most of the universe lies beyond horizons we cannot cross. Knowledge at the largest scales is bounded not by ignorance alone, but by the structure of space-time itself. This realization has implications for how we interpret cosmological models. When scientists speak of the curvature of space, the fate of the universe, or the possibility of a multiverse, they are often making inferences based on the narrow window of the observable cosmos. These inferences are robust within their domain, but we must recognize their contingency. If the universe is infinite, we will never confirm it. If it has exotic structures beyond our horizon, we may never know. The largest scales invite theories that may be testable only in limited ways, forever constrained by the walls of causality. Cosmic horizons also have a thermodynamic aspect. In the 1970s, physicists studying black hole thermodynamics found that horizons carry entropy, a measure of information. Jacob Bekenstein and Stephen Hawking showed that the entropy of a black hole is proportional to the area of its horizon, not its volume. This insight suggested a radical idea. Horizons themselves encode information about the regions they enclose. The so-called holographic principle, proposed later by Gerard 't Hooft and Leonard Susskind, extends this notion, suggesting that the information content of a region of space can be described by data inscribed on its boundary. If true, horizons are not only limits to observation, but repositories of knowledge in ways we do not yet fully understand. This interplay between horizons, information, and knowledge reaches into the heart of modern theoretical physics. The black hole information paradox, the holographic principle, and the study of cosmological horizons suggests that what we mean by knowledge may itself require redefinition at cosmic scales. Knowledge may not be about peering deeper into the interior of reality, but about understanding the relationships encoded on horizons themselves. Our maps may be written on boundaries, not in the depths, reshaping how we think about the territory of the cosmos. Beyond physics, horizons have a philosophical resonance. They remind us that knowledge is not infinite, that there are built-in boundaries beyond which we cannot go. These are not temporary obstacles waiting to be overcome by new instruments, but permanent features of the universe. Just as the uncertainty principle sets limits at the smallest scales, cosmic horizons set limits at the largest. Together, they frame the human pursuit of knowledge between two walls, the quantum and the cosmic, leaving us to explore the vast but finite territory in between. And yet, these boundaries do not render the quest futile. The observable universe is still unimaginably rich, containing hundreds of billions of galaxies, each with hundreds of billions of stars. Within our horizon, there is more than enough mystery to occupy human curiosity for millennia. Moreover, the very discovery of horizons is itself a triumph of knowledge. To know that there are limits is to know something profound about the universe. The recognition of boundaries is not ignorance, it is a form of understanding. Perhaps, then, horizons are not only barriers but also mirrors. They reflect back to us the nature of our own quest for knowledge. We strive to know everything, yet the universe shows us that totality is beyond reach. We desire certainty, yet the cosmos answers with limits. To live within horizons is to live with both wonder and humility, knowing that beyond the visible sky there are realms forever out of view. And maybe it is precisely this tension between what we can see and what we cannot, that gives the human search for knowledge its endless vitality. Chapter 5. Complexity and chaos when knowing isn't predicting. The dream of science, especially in its classical age, was to reveal a universe governed by perfect laws, capable of predicting every event if only enough information were known. Newton's mechanics suggested that the motion of a planet could be calculated with exactitude centuries into the future. Laplace imagined a mind, his famous demon, that, knowing all positions and velocities at a given instant, could compute the past and future with perfect clarity. This vision of determinism dominated scientific thought for centuries, shaping not only physics but also philosophy and even social theory. Yet, as scientists pushed into the study of complex systems, they discovered that determinism does not always yield predictability. Orderly rules can produce behavior that appears random, and small uncertainties can grow into overwhelming unpredictability. This insight gave rise to chaos theory, which revealed that even simple deterministic equations can generate outcomes that defy long-term forecasting. Chaos does not mean disorder in the colloquial sense, nor does it imply the absence of laws. Rather, it describes a sensitivity to initial conditions so extreme that small differences grow exponentially with time. In such systems, knowing the rules is not enough. Precise knowledge of starting conditions is also required, and since no measurement can be infinitely precise, predictions eventually fail. Chaos shows us that determinism and predictability are not the same thing. One of the earliest and most striking illustrations of chaos came from meteorology. In the 1960s, Edward Lorenz, studying simplified models of weather, discovered that tiny differences in input values produced dramatically different forecasts. He realized that rounding a number in his program, a difference so small as to seem negligible, led to divergent outcomes. This sensitivity became famous as the butterfly effect, the idea that the flap of a butterfly's wings might influence the course of a tornado weeks later. While not meant literally, the metaphor captures the reality that weather is a chaotic system where long-term forecasts are inherently limited. No matter how powerful our computers or how detailed our models, there will always be a horizon beyond which precise prediction becomes impossible. Chaos is not confined to weather. It appears in many natural systems, the orbits of asteroids perturbed by planetary gravitation, the flows of fluids, the dynamics of ecosystems, even the rhythms of the human heart. What unites these systems is nonlinearity, the principle that outputs are not simply proportional to inputs. In linear systems, doubling a cause doubles its effect. In nonlinear systems, small causes can have disproportionate effects, or large inputs may saturate without producing commensurate outcomes. Nonlinearity opens the door to feedback loops, tipping points, and emergent behavior. It is the hallmark of complexity. Complexity science extends beyond chaos to encompass the study of systems made up of many interacting parts. Unlike isolated particles moving according to simple laws, complex systems exhibit collective behavior that cannot be easily reduced to the properties of their components. An ant colony, for instance, is composed of individuals following simple behavioral rules, yet the colony as a whole achieves feats of engineering, navigation, and resource management. The intelligence of the colony emerges from the interactions, not from any single ant. Similarly, the human brain consists of billions of neurons, each obeying electrochemical principles. Yet consciousness arises not from individual neurons, but from the patterns of activity across the network. The study of emergent phenomena highlights a central lesson. Knowing the rules does not guarantee knowing the outcome. In principle, we may understand the molecular interactions of water, but predicting the exact path of a turbulent eddy in a river remains beyond reach. We may know the genetic code, yet forecasting the development of an entire organism from that code alone is immensely challenging. Complexity introduces levels of organization that require new descriptions and new laws. Biology cannot be fully reduced to chemistry, nor chemistry to physics. Each level brings its own patterns, irreducible to the lower levels, even though they are consistent with them. One striking example is the phenomenon of phase transitions. When water freezes or boils, a collective shift occurs among its molecules, producing new macroscopic properties. These transitions can be studied statistically, using the mathematics of large numbers, but predicting the exact details of each molecular motion is unnecessary and impossible. Similarly, in magnetism, countless atomic spins align to produce large-scale order. Here, complexity produces simplicity at higher levels, but only after turbulent and chaotic processes at smaller scales. Predictability emerges in the large, even as unpredictability rules the small. Complexity also reshapes our understanding of causality. In linear systems, causes and effects can be traced clearly. In complex systems, causality can loop back on itself. Feedback amplifies or dampens effects, making it difficult to isolate single causes. Climate change, for instance, involves feedback mechanisms where warming melts ice, reducing reflectivity and causing further warming. Forest ecosystems, economic markets, and social networks all display similar feedback dynamics. These loops make long-term behavior difficult to predict with certainty, even when individual interactions are well understood. The limits imposed by chaos and complexity are not simply practical but fundamental. Even with perfect models and infinite computing power, unpredictability remains. Lorenz's work showed that deterministic equations can produce outcomes indistinguishable from randomness. This challenges the classical dream of total knowledge. We may know the laws, but still lack the power to foresee the future with unlimited accuracy. Prediction horizons emerge not because of ignorance, but because of the inherent structure of nonlinear dynamics. Yet, unpredictability does not mean futility. Chaos and complexity often yield patterns of order within apparent disorder. Strange attractors, fractal structures, and statistical regularities reveal hidden forms of predictability. A double pendulum may swing unpredictably in detail, but its motion is confined within a structured space of possibilities. Weather forecasts may fail beyond 2 weeks, but climate models can capture long-term averages and trends. Chaos is bounded, and within its bounds new forms of knowledge are possible. This boundedness has inspired new approaches to science. Rather than seeking perfect prediction, complexity science often aims at understanding distributions, probabilities, and resilience. Instead of asking where each bird in a flock will fly, we ask how flocking behavior emerges, what rules govern its stability, and how it adapts to disturbances. Instead of predicting each stock market move, economists study systemic risk, volatility, and the potential for cascading failures. Knowledge shifts from the precise to the statistical, from forecasting individual events to understanding collective dynamics. Complexity also encourages humility in applying scientific knowledge. In systems where small changes produce disproportionate outcomes, interventions can have unintended consequences. Introducing a new species to control pests can destabilize an ecosystem. Economic policies can trigger unexpected cascades in global markets. Medical treatments can alter microbial communities in ways that ripple through the body. Complexity teaches us to anticipate surprises, to test scenarios, and to design systems with buffers and adaptability. The rise of computational power has revolutionized the study of complex systems. Simulations allow scientists to explore scenarios that are analytically intractable. Cellular automata, agent-based models, and network simulations reveal how simple rules can generate intricate outcomes. The famous Game of Life, devised by John Conway, shows how a grid of simple on-off rules can produce astonishingly complex patterns, even self-replicating structures. Though artificial, these simulations echo the behavior of real-world systems, where local interactions produce global phenomena. In recent decades, complexity science has become central to disciplines ranging from ecology to economics, neuroscience to computer science. It provides tools to study epidemics, power grids, financial systems, and the internet. Each of these domains involves networks of interactions where unpredictability coexists with structure. Complexity does not abolish knowledge but reframes it. The emphasis shifts from prediction to understanding, from control to adaptation, from certainty to probability. The philosophical implications are profound. If knowing the laws of nature does not guarantee prediction, then the relationship between knowledge and power must be reconsidered. Science remains extraordinarily effective, but its effectiveness lies in characterizing patterns, tendencies, and probabilities rather than in producing exact forecasts. The dream of Laplace's demon fades, replaced by a vision of knowledge that is partial, contextual, and dynamic. There is a certain resonance here with earlier limits. Quantum uncertainty set boundaries at the smallest scales. Cosmic horizons define boundaries at the largest. Complexity and chaos reveal boundaries in between, where the collective behavior of many parts resists precise prediction. These are not failures of science, but revelations of nature's richness. They remind us that reality is not a machine unfolding with clockwork precision, but a tapestry of interactions, sensitive, adaptive, and open-ended. At an existential level, this recognition reshapes our understanding of life itself. Human societies are among the most complex systems known, filled with feedback loops, emergent norms, and unpredictable cascades. To expect perfect foresight in human affairs is to ignore the lessons of chaos and complexity. And yet, within unpredictability lies resilience, creativity, and adaptation. Perhaps it is the very unpredictability of complex systems that makes life dynamic and history meaningful. We are left, then, with a humbler but richer conception of knowledge. To know is not always to predict. Sometimes it is to recognize patterns without foreseeing details, to map possibilities without charting exact paths. In this sense, the study of complexity brings us closer to the spirit of science itself. a balance of rigor and humility, law and uncertainty, explanation and mystery. The world at its most intricate scales invites us to learn without the promise of total prediction. And perhaps that is enough. The unpredictability of complex systems may frustrate the dream of absolute control, but it also ensures that the universe remains a place of surprise. We may never foresee every storm, every heartbeat, every fluctuation of life and society. But in that uncertainty lies vitality. The limits of prediction remind us that the future is not fully written, that possibility itself is woven into the structure of reality. Chapter 6. Gödel, Turing, and the Limits of Logic. The pursuit of knowledge has long rested on the conviction that the universe, and by extension human thought, can be rendered in terms of logical order. Since the time of Aristotle, logic has been the scaffolding upon which philosophy and science have been built. The hope was that, if reasoning could be systematized, truth itself might be made fully transparent. In the modern era, this vision gained new force with the development of symbolic logic and mathematics. The 19th century witnessed an extraordinary effort to place all of mathematics on a rigorous foundation, to show that every mathematical truth could be derived from a finite set of axioms and rules of inference. If successful, this project would have offered not just certainty but completeness. A map of mathematical reality in which every statement could be classified as true or false. For a time, this dream seemed achievable. Mathematicians such as Gottlob Frege, David Hilbert, and Bertrand Russell sought to formalize mathematics as a perfectly consistent logical system. Hilbert, in particular, declared that in mathematics there is no ignoramus, no unknowable. He believed that every mathematical problem could, in principle, be solved, given sufficient effort and formal rigor. His program aimed to prove both the consistency and completeness of mathematics, that the axioms were free of contradiction, and that every true statement could be derived within the system. It was a vision of absolute order, echoing the determinism of Laplace, but applied not to nature, but to the abstract realm of thought. The shock came in 1931, when a young Austrian mathematician named Kurt Gödel published his incompleteness theorems. With exquisite precision, Gödel demonstrated that Hilbert's dream was unattainable. Any sufficiently powerful formal system of arithmetic, one capable of expressing basic properties of numbers, cannot be both complete and consistent. There will always exist statements that are true but cannot be proven within the system. And if one extends the system to capture those truths, new unprovable truths will emerge. The landscape of mathematics, Gödel showed, is inexhaustible. Gödel's proof relied on a brilliant technique, self-reference. By encoding statements about mathematics into numbers, a method known as Gödel numbering, he was able to construct a statement that essentially says this statement cannot be proven within this system. If the system could prove the statement, it would be inconsistent. If the system could not, then the statement would be true but unprovable. In either case, the hope of a complete, consistent formal system was dashed. The very logic designed to guarantee certainty revealed its own limits. The implications were profound. Mathematics, long seen as the epitome of certainty, turned out to harbor inherent mysteries. The incompleteness theorems did not undermine the reliability of mathematics in practice. Engineers and physicists continued to use equations with extraordinary success, but they showed that the quest for a final fountain was doomed. There is no ultimate set of axioms from which all truths can be deduced. Mathematical knowledge is necessarily open-ended. Around the same time, another figure was uncovering a related limit in the realm of computation. Alan Turing, working in the 1930s, sought to clarify what it means for a problem to be computable. He devised the concept of a universal machine, a theoretical device that could read symbols on a tape, follow a finite set of rules, and manipulate the symbols step by step. This Turing machine became the foundation of modern computer science. But Turing also showed that there are problems no machine can solve. The most famous of these is the halting problem. Turing asked whether there could exist a general algorithm that, given any computer program and any input, could determine whether the program would eventually halt or run forever. He proved that no such algorithm exists. There will always be programs for which the halting behavior cannot be decided. This result paralleled Gödel's incompleteness in logic. Just as mathematics cannot be complete, computation cannot be universal. There are limits to what can be decided, even in principle. The halting problem is not merely a curiosity. It reveals that undecidability is woven into the fabric of computation. Some problems cannot be solved by any algorithm, no matter how much time or memory is available. For example, determining whether certain mathematical conjectures can be resolved within given axioms may reduce to undecidable questions. In computer science, questions about software verification, program equivalence, and system reliability often brush against these boundaries. Engineers can prove correctness in many cases, but not universally. The dream of a perfect, all-encompassing algorithm, like Hilbert's dream of a complete mathematics, dissolves in the face of these results. Taken together, Gödel's and Turing's discoveries mark a turning point in the history of knowledge. They show that limits exist not only in physics, where quantum uncertainty and cosmic horizons impose boundaries, but also in the abstract realms of logic and thought. Even within the idealized world of symbols and rules, where physical constraints like noise and measurement do not apply, absolute completeness remains out of reach. Knowledge has boundaries in principle, not only in practice. Philosophers and scientists have debated the deeper meaning of these results. Some see them as an invitation to humility, a recognition that human knowledge, however vast, will always leave questions unanswered. Others see them as a spur to creativity. If no system is complete, then there will always be room for new axioms, new models, new approaches. Mathematics and computation are not static, but evolving, open to extension and reinterpretation. The boundary is not a wall, but a horizon, always receding as we advance. There are also reflections on the human mind. Could Gödel's theorems apply to human cognition? If the brain is itself a kind of computational system, then perhaps it too is limited by undecidability. Yet some thinkers, including Roger Penrose, have speculated that human consciousness might transcend formal systems, that the mind may perceive truths inaccessible to algorithmic reasoning. Others caution that such arguments risk romanticizing human thought and misinterpreting Gödel's results. Whether the mind surpasses machines or not, the theorems remind us that even the purest reasoning has edges it cannot cross. The legacy of Gödel and Turing extends deeply into computer science and technology. Modern encryption relies on the difficulty of certain computational problems, many of which border undecidability. Complexity theory, which classifies problems by their difficulty, grew from the recognition that not all problems are solvable. Quantum computing, despite its promise of extraordinary power, does not erase the boundaries imposed by undecidability. Even with quantum algorithms, the halting problem remains undecidable. Limits persist, no matter how advanced the machinery. There is also an aesthetic dimension to these discoveries. Gödel's theorems show that mathematics is inexhaustible, always unfolding new vistas. This incompleteness can be seen not as a failure, but as a kind of richness. There will always be new truths beyond current systems, new questions to pursue. Turing's work reveals that the landscape of computation is infinite, with regions accessible and others forever closed. The impossibility of universal algorithms means that creativity, adaptation, and heuristics remain essential. Knowledge is not a final edifice, but an endless exploration. At a broader scale, these results resonate with themes across science. The uncertainty principle in quantum mechanics, the unpredictability of chaotic systems, and the cosmic limits of horizons all show boundaries to knowledge in the physical universe. Gödel and Turing revealed that similar boundaries exist in the abstract realm of logic. Together, they suggest a profound truth. Limits are not accidental, not the result of current ignorance, but essential features of reality and reasoning. Still, it is important to distinguish these limits from futility. Science and mathematics remain astonishingly powerful. Within their domains, they yield precision, prediction, and technology that transform the human condition. The limits revealed by Gödel and Turing do not undermine this power. They place it in context. They remind us that the search for knowledge is infinite, that there will always be truths beyond our reach, problems beyond our algorithms, mysteries that remain unresolved. And perhaps that is where the deepest meaning lies. For centuries, humans imagined a future of total knowledge, where nothing would remain hidden. But the discoveries of the 20th century revealed a different vision. A universe where knowledge is inexhaustible because it is incomplete. Incompleteness does not weaken the quest, it ensures its continuation. We will never finish the map, and that is precisely why the journey endures. At the edge of logic, we find not despair but a strange kind of beauty. To know that some truths can never be proven, some problems never solved, is to realize that mystery is not only in the stars or in the quantum vacuum, but also in the silent symbols of mathematics itself. Even in the realm of perfect abstraction, we encounter limits, horizons, and unknowns, and in recognizing them, we glimpse a truth that unites science and philosophy alike. That knowledge is not about conquering all mystery, but about dwelling within it, moving forward while knowing the path will never end. Chapter 7. The Boundaries of the Brain. The human brain is often described as the most complex structure known in the universe. Composed of roughly 86 billion neurons, each forming thousands of connections, it orchestrates perception, memory, language, and imagination. It produces not only our capacity for science, but also our awareness of the limits of science. In many ways, the brain is both the instrument and the subject of inquiry, a paradoxical situation in which the organ doing the knowing attempts to know itself. Yet as neuroscience has advanced, it has become increasingly clear that the brain imposes boundaries on its own capacities. These boundaries shape the horizon of human knowledge, just as surely as quantum uncertainty shapes the microscopic world and cosmic horizons shape the universe at large. At the most basic level, the brain is limited by its biology. It is the product of millions of years of evolution, optimized not for truth in the abstract, but for survival and reproduction. Our senses capture only a narrow slice of the electromagnetic spectrum and the acoustic range. Our working memory can juggle only a handful of items at once. Our attention is easily distracted, our reasoning biased, and our intuitions shaped by patterns that helped our ancestors navigate savannas, rather than parse quantum field equations. In this sense, our cognitive architecture is constrained from the outset. The brain was not designed to comprehend the totality of the cosmos, but to secure food, shelter, and social bonds. Scientific knowledge represents an extraordinary extension of this architecture, yet it remains grounded in its limitations. Consider working memory. Studies show that most people can hold about 7 items in immediate consciousness at once, sometimes fewer. This cognitive bottleneck means that complex reasoning often requires external aids, writing, diagrams, symbolic systems, to extend the brain's reach. Mathematics, for instance, can be seen as a technology for outsourcing thought, allowing us to track relationships far beyond what working memory could manage alone. Language serves a similar role, making it possible to structure and transmit ideas across individuals and generations. These tools expand cognition, but the underlying constraints remain. Without them, the raw capacity of the brain is sharply bounded. The brain is also prone to systematic biases. Cognitive psychology has cataloged dozens of heuristics that shape judgment: confirmation bias, availability bias, anchoring effects, and many others. These shortcuts are efficient for navigating uncertain environments, but they distort reasoning when applied to abstract problems. They reveal that the brain is not a neutral mirror of reality, but a fallible, adaptive organ. Even when we strive for objectivity, our thoughts are colored by context, framing, and emotion. Knowledge is filtered not only through sensory limits, but through biases embedded in neural processing itself. Neuroscience has illuminated some of the physical underpinnings of these boundaries. The brain consumes about 20% of the body's energy, a striking demand for an organ weighing only about 3 pounds. This energy budget constrains the number of neurons, their firing rates, and the redundancy of circuits. Evolution has favored efficiency, not infinite capacity. Neurons operate in networks that balance metabolic cost against computational power. Thus, limits in memory, attention, and processing speed are not arbitrary. They are consequences of physical trade-offs in energy, space, and time. Even with these constraints, the brain achieves remarkable feats through plasticity. Neural circuits can reorganize in response to experience, injury, or learning. Musicians develop enlarged representations of finger movements. Bilingual speakers show altered connectivity in language areas. Stroke patients can sometimes regain functions through rerouting of pathways. Plasticity shows that the brain is not a fixed machine but a dynamic system, reshaping itself throughout life. Yet plasticity has limits. Recovery is rarely complete after major damage, and certain critical periods in development set boundaries on what can be acquired later. A child deprived of language in early years cannot fully recover linguistic capacity in adulthood. The brain is flexible, but not without end. Perhaps the most intriguing boundary lies in the question of whether the brain can fully understand itself. To model a system as complex as the human brain may require a system of equal or greater complexity. But the brain is both the object and the tool of inquiry. This raises a puzzle of self-reference reminiscent of Gödel's incompleteness. Can a system contain a complete account of itself? Some philosophers argue that consciousness may be an example of cognitive closure, a domain inaccessible to the very organ that produces it. Just as a mouse cannot understand calculus, perhaps the human brain cannot fully grasp the mechanisms of subjective experience. Consciousness remains one of the deepest mysteries of neuroscience. While much is known about neural correlates of awareness, the activity patterns associated with perception, decision, and self-report, the subjective quality of experience, The so-called hard problem resists explanation. Why should electrochemical activity give rise to the sensation of color, the feeling of pain, the awareness of self? Some scientists believe that continued progress in neuroscience will eventually dissolve the mystery, reducing consciousness to mechanisms. Others suspect that the human mind may never fully penetrate this question, because it involves the brain trying to illuminate its own intrinsic perspective. The boundaries of the brain are also evident in its temporal nature. Neural processing operates on scales of milliseconds, but consciousness integrates information over longer intervals. This means our perception of reality is always slightly delayed, a smoothed version of events stitched together from fragments. Experiments show that the brain often predicts and fills in sensory information rather than presenting an exact real-time stream. Our awareness is less a mirror of the external world than a reconstruction, optimized for coherence rather than accuracy. This limitation shapes our very sense of time and presence. Another domain of limitation lies in memory. Human memory is not a faithful recording, but a reconstructive process. Each recollection is a blend of stored fragments, context, and imagination. Memories can be distorted, implanted, or forgotten. While this plasticity allows for creativity and adaptation, it also means that our knowledge of the past is inherently fallible. Even personal identity, grounded in remembered continuity, is subject to the boundaries of neural storage and reconstruction. Advances in artificial intelligence and neurotechnology raise new questions about these boundaries. Brain-computer interfaces can now translate neural signals into control of prosthetic limbs or computer cursors. Neuroimaging can decode aspects of visual perception or imagined speech. Yet these technologies still capture only a fraction of brain activity, and their interpretations are limited by models built on statistical correlations. The complexity of neural dynamics far exceeds current computational capacity. While machines may augment or extend cognition, they do not erase the fundamental limits of the biological brain. Comparative neuroscience also highlights boundaries by contrast. Other species excel in domains where humans are limited. Birds can navigate across continents using cues we barely comprehend. Bats echolocate with precision beyond human hearing. Octopuses exhibit problem-solving with radically different neural architectures. These examples remind us that human cognition, for all its power, is only one variant of neural design. Our boundaries are not universal boundaries, but species-specific contours of mind. The recognition of these limits has philosophical implications. If the brain cannot fully know itself, then some questions may remain permanently open. The structure of subjective experience, the ultimate roots of creativity, the essence of free will, these may resist reduction to neural terms. This does not mean they are mystical or supernatural, but that they may be inaccessible to the tools evolution has given us. Knowledge, in this view, is bounded not only by the external world, but by the architecture of the knower. Yet neuroscience also shows that boundaries need not be barriers to progress. By understanding limits, we can design strategies to work around them. Writing, mathematics, art, and science itself are cultural technologies that extend cognition beyond biological constraints. Collaboration allows societies to pool knowledge far beyond the reach of any individual. Computers augment memory and calculation. Instruments expand perception into ranges the brain cannot directly sense. Each of these is a scaffold that allows a limited brain to participate in projects of virtually unlimited scale. Still, the scaffolds themselves depend on the brain's capacity to use them. A telescope reveals distant galaxies, but only a brain can interpret the image. A supercomputer processes data, but only a brain can assign meaning. The limits of the brain thus remain foundational, even as they are extended by culture and technology. Ultimately, knowledge is filtered through the neural substrate of thought. The boundaries of the brain are the boundaries of human experience. At an existential level, this recognition is sobering. The brain, for all its wonders, is fragile. It ages, it suffers injury and disease, it is altered by trauma and chemicals. Memory fades, perception blurs, cognition slows. Even the greatest works of thought emerge from neurons vulnerable to entropy. Yet within this fragility lies a paradoxical strength. That such a finite organ can contemplate infinity, that such a bounded system can explore the vast cosmos, is itself astonishing. The boundaries of the brain do not diminish the quest for knowledge, they define it. And perhaps that is the lesson. Just as horizons mark the edge of the visible universe, the brain's limits mark the edge of human understanding. To recognize those limits is not defeat, but wisdom. It means that knowledge will always be partial, situated, and human. Yet within those boundaries, we have painted galaxies, split atoms, written symphonies, and asked the deepest questions. The brain may be bounded, but within its boundaries lies a universe of thought. Chapter 8. The Simulation of Knowledge, AI and Machines. For much of human history, knowledge was considered uniquely human, inseparable from the capacity for thought, language, and self-reflection. The tools we built, stone axes, telescopes, microscopes, extended perception, but did not themselves embody knowledge. They were instruments, not thinkers. Yet in the modern age, machines have begun to blur this distinction. With the advent of artificial intelligence, we now confront entities that can process vast amounts of information, recognize patterns, and generate outputs that resemble reasoning. These systems simulate knowledge, and in doing so, they raise profound questions about what knowledge itself is, and whether machines can ever truly possess it. Artificial intelligence is not a single technology, but a collection of methods that enable machines to perform tasks associated with human cognition. Early AI in the mid-20th century was based on symbolic approaches. Researchers attempted to encode rules of logic and inference into machines, imagining that if enough rules were specified, a computer could reason like a person. This good old-fashioned AI demonstrated early successes in domains such as theorem proving and game playing, but it faltered in the face of real-world complexity. Encoding common sense, ambiguity, and contextual nuance proved insurmountable. The resurgence of AI in recent decades has been driven by machine learning, particularly neural networks inspired by the architecture of the brain. Unlike symbolic systems, neural networks do not rely on explicit rules. Instead, they adjust internal connections in response to data, learning to map inputs to outputs through statistical association. Given enough data, such systems can recognize objects and images, transcribe speech, translate languages, and even generate human-like text. These achievements often appear indistinguishable from genuine knowledge. Yet at their core, machine learning systems are statistical engines, not conscious reasoners. They simulate patterns of knowledge without necessarily understanding them. This raises the crucial distinction between simulation and comprehension. When a large language model generates a passage of text about physics, it does so by predicting sequences of words that are statistically likely given its training data. The result may be coherent, accurate, and even insightful. But does the system know what it is saying? Most researchers argue that it does not. Knowledge, in the human sense, involves grounding in experience, intention, and meaning. Machines process symbols without intrinsic understanding. They manipulate form but lack content. Philosophers have long debated this distinction. In the 1980s, John Searle introduced the Chinese room thought experiment. Imagine a person inside a room, following instructions for manipulating Chinese characters without knowing Chinese. To an outside observer, the room appears to converse fluently, but inside there is no understanding, only rule following. Searle argued that AI systems, no matter how convincing, function like the Chinese room. They simulate understanding without possessing it. Critics countered that understanding might emerge at the level of the whole system, not the individual rules. But the debate underscores the ambiguity between simulation and knowledge. Despite this ambiguity, AI has become indispensable in science and technology. Algorithms analyze genomic data, detect exoplanets in astronomical observations, and predict protein structures with unprecedented accuracy. In many cases, AI systems discover patterns that elude human researchers. AlphaFold, developed by DeepMind, solved a problem in molecular biology that had stymied scientists for decades. Yet even here, the system does not know proteins in the way a biochemist does. It cannot explain its reasoning in human terms, nor does it situate its discoveries within a broader conceptual framework. It produces correct answers without insight. This opacity introduces new challenges. AI systems, especially deep learning models, are often described as black boxes. They produce outputs that work but cannot be fully traced to comprehensible reasoning. For fields that rely on explanation, this lack of transparency is troubling. Scientific knowledge is not only about prediction but also about understanding why. If machines generate results without interpretable pathways, are they expanding knowledge or merely generating useful approximations? The line between knowledge and simulation blurs further. There are also limits inherent in AI itself. While machines can process immense data sets, they remain constrained by the quality and scope of their inputs. Biases in training data lead to biases in output. Models trained on incomplete or skewed information reproduce those distortions. Furthermore, AI lacks the embodied grounding that shapes human cognition. Humans learn language in the context of sensory experience, social interaction, and physical engagement with the world. Machines learn from data detached from direct experience. This difference may impose fundamental constraints on machine knowledge. Some theorists suggest that true artificial understanding would require embodiment, robots that interact with the world through perception and action, learning not only from text but from lived experience. Others argue that understanding is not about embodiment, but about the capacity to integrate and generalize across domains. The debate reflects deeper uncertainty about what knowledge ultimately requires. Is it statistical correlation, symbolic reasoning, subjective awareness, or some combination? The limits of machines echo, in some respects, the limits revealed by Gödel and Turing. Just as there are undecidable problems in logic and uncomputable functions in mathematics, there may be forms of knowledge beyond the reach of AI. Some tasks may resist automation not because they are complex, but because they are undecidable in principle. Moreover, even if machines could simulate every aspect of human reasoning, the question of whether they understand remains unresolved. Knowledge in its fullest sense may involve qualities, consciousness, intentionality, meaning, that machines cannot replicate. At the same time, the power of simulation should not be underestimated. In practice, simulation is often enough. Weather forecasts, medical diagnoses, financial predictions, each depends on models that are approximations rather than complete truths. If machines can simulate knowledge well enough to guide action, they serve a functional role akin to knowledge. The boundary between simulation and knowledge becomes less clear when the outcomes are useful, reliable, and transformative. There is also the question of whether human knowledge itself is, in some sense, a simulation. The brain constructs models of the world based on sensory input and prior experience. Perception is not a direct apprehension of reality, but a predictive reconstruction. If so, then human knowledge may also be a simulation, albeit one with grounding in biological experience. In this light, the difference between humans and machines may be of degree rather than kind. Both build models. The question is how those models are grounded and interpreted. As AI advances, these questions grow increasingly urgent. Machines now generate art, compose music, and write text that evokes creativity. Yet whether this creativity is genuine or imitative remains debated. When a neural network produces a painting in the style of Van Gogh, is it creating or recombining? When a language model generates an essay, is it reasoning or mimicking? The simulation of knowledge forces us to confront the boundaries of our definitions. Perhaps knowledge is less a property of a system and more a relational quality between systems and their environments. AI also challenges our sense of uniqueness. For centuries, humans believed that certain faculties, reason, language, creativity, set us apart. Each advance in AI erodes this distinction, showing that machines can replicate tasks once thought uniquely human. This does not mean machines possess consciousness or self-awareness, but it does compel us to rethink what knowledge means in a world where simulation can be so convincing. Ethical implications arise as well. If machines simulate knowledge without understanding, they can still influence decisions with profound consequences. Algorithms in medicine, law, and finance already shape human lives. Their simulation of knowledge becomes functionally equivalent to knowledge in practice, even if philosophically distinct. The risk is that we may overestimate machine understanding, attributing authority to systems that do not, in fact, know. In considering the boundaries of machine knowledge, we also confront our own. If humans cannot fully define knowledge, how can we determine whether machines possess it? The debate about artificial intelligence mirrors the broader question of whether knowledge itself is ever more than an approximation, a simulation we trust because it works. Machines may not resolve this question, but they illuminate it by forcing us to articulate what we mean by knowing. Perhaps the ultimate boundary is not technological but conceptual. The difference between simulation and knowledge may be less about machines than about our definitions. If knowledge is functional, then machines already possess it. If knowledge requires consciousness, then perhaps they never will. Either way, the simulation of knowledge by machines has already transformed human understanding, creating a new landscape where the boundaries of thought, reality, and meaning blur. And here, again, we find an existential reflection. The machines we have built mirror us, not in their biology, but in their capacity to simulate. They remind us that much of what we call knowledge may itself be a simulation, patterns of thought shaped by survival, not by ultimate truth. If machines can simulate knowledge convincingly, perhaps it is because we too live by simulations. To recognize this is not to diminish humanity, but to deepen our sense of what it means to know, to build maps, models, and meanings in a universe that may never yield its full territory. Chapter 9. The Final Mysteries. As science has expanded its reach, it has solved countless problems once thought impenetrable. Diseases that devastated populations have been understood and controlled. The motions of planets, once puzzling, are now predicted with exquisite accuracy. The structure of matter, the dynamics of energy, and the origins of stars have all yielded to human inquiry. Yet even as progress continues, certain questions remain that resist resolution. These are not puzzles of detail, awaiting only better instruments or more data. They are mysteries at the heart of existence, questions that seem to demand answers yet offer little foothold for solution. At the edge of knowledge, these final mysteries stand like mountains on the horizon, immovable, awe-inspiring, and perhaps unreachable. One of the deepest of these is consciousness. Neuroscience has revealed much about the brain. The firing of neurons, the networks of synapses, the rhythms of electrical activity that underlie perception and action. Yet the subjective quality of experience, the redness of red, the ache of pain, the awareness of self, remains unexplained. How does matter give rise to mind? This so-called hard problem of consciousness has been debated for decades. Some researchers believe it will eventually dissolve into neuroscience, with subjective experience explained as emergent from neural computation. Others suspect that consciousness points to something fundamentally new, a property not reducible to existing frameworks. For now, it remains a mystery, not whether consciousness exists, we live it every moment, but how and why it arises at all. Another mystery lies at the opposite end of the spectrum, the origin of the universe itself. Cosmology has traced the expansion of the universe back to a hot, dense state we call the Big Bang, nearly 13.8 billion years ago. But what preceded it, if anything? Was the Big Bang the beginning of time or a transition from something earlier? Current physics cannot answer with certainty. Quantum cosmology suggests scenarios where universes arise from fluctuations, or where time itself is emergent rather than fundamental. Some theories propose cycles of expansion and contraction, others a multiverse in which countless universes bubble into existence. Yet these ideas, however compelling, remain speculative. The ultimate origin, the reason there is something rather than nothing, remains elusive. Linked to this is the mystery of why the universe seems so finely tuned for life. The values of fundamental constants, such as the strength of gravity, the charge of the electron, or the ratio of forces in the nucleus, fall within narrow ranges that allow stars, planets, and chemistry to exist. Change them slightly, and the universe might collapse or disperse without structure. Is this fine-tuning a coincidence, a necessity, or evidence of a multiverse in which many universes exist with different parameters, and we find ourselves in the one that permits life? The anthropic principle suggests that we should not be surprised to find the universe compatible with our existence, but this is less an explanation than a reflection. The deeper reason remains hidden. Another final mystery. A further enigma concerns the nature of time. We experience time as a flow, a succession of moments moving from past to future. Yet physics often describes time as a dimension, akin to space, where past, present, and future coexist in a four-dimensional block. If this is true, then our sense of flow may be an illusion generated by the brain. But why should the universe contain this asymmetry between past and future at all? The laws of physics are largely time-symmetric. They work the same forwards and backwards. Yet entropy increases. Memories are formed of the past and not the future, and causality runs in one direction. The arrow of time is deeply tied to the second law of thermodynamics. But why the universe began in a state of low entropy remains unanswered. The flow of time, one of the most immediate aspects of experience, conceals profound questions about the structure of reality. Another enduring mystery is dark matter and dark energy. Observations of galaxies and cosmic expansion reveal that ordinary matter, the atoms that make up stars, planets, and people, accounts for only a small fraction of the universe. The rest is dark, invisible matter that exerts gravitational pull, and dark energy that drives cosmic acceleration. Despite decades of study, their nature is unknown. Dark matter could be exotic particles not yet detected, or it might represent a modification of gravity at galactic scales. Dark energy could be a cosmological constant or a dynamic field. Each possibility carries profound implications for the fate of the universe. But until these are understood, we live in a cosmos whose dominant components remain mysteries. There are also mysteries that touch directly on human existence. Free will, for instance, remains unsettled. Neuroscience suggests that decisions may be initiated by unconscious processes before we are aware of them. Physics, whether deterministic or probabilistic, leaves little room for the kind of absolute freedom once imagined. Yet our lived experience insists on choice, responsibility, and agency. Reconciling these perspectives, subjective freedom and objective causation, remains unresolved. Is free will an illusion, a useful construct, or something more fundamental than our current science can describe? Mysteries extend into mathematics as well. Gödel showed that formal systems contain unprovable truths, but deeper questions persist. Why does mathematics describe the physical world so effectively? Is mathematics discovered, existing independently of minds, or invented, a creation of human cognition? If mathematics is discovered, then it suggests a Platonic realm of truths beyond space and time. If invented, then the fact that it aligns so well with physics is uncanny. This relationship between mathematics and reality remains an enigma at the foundations of science. The ultimate fate of the universe is another question with no definitive answer. Cosmology offers scenarios: a heat death in which entropy reaches a maximum and all structure dissipates, a big crunch where expansion reverses, a big rip where dark energy tears everything apart, or endless inflation spawning new universes. Each scenario is consistent with some interpretation of current data, yet none is confirmed. The distant future, like the distant past, lies beyond certainty. We know that stars will fade, galaxies will drift apart, and black holes will eventually evaporate. But whether existence itself ends or transforms into something else is unknown. Each of these mysteries highlights a boundary where human knowledge meets its edge. In some cases, the edge is practical. Our instruments cannot yet probe dark matter, or our theories cannot yet unify quantum mechanics and relativity. In other cases, the edge may be principled: the origin of existence, the nature of consciousness, the ultimate why of reality. The challenge is that science thrives on testable hypotheses, yet some of these questions resist direct test. We may infer, model, and speculate, but the answers may forever lie just beyond reach. Yet the presence of final mysteries does not diminish science, it defines it. If everything were known, inquiry would cease. It is the presence of the unknown that propels investigation, drives curiosity, and ensures that knowledge remains a living process. Even if consciousness resists explanation, probing it deepens neuroscience. Even if dark energy's nature remains hidden, measuring its effects refines cosmology. The pursuit of mystery is itself a form of knowledge, an acknowledgement that we exist within a universe far larger than our current understanding. At the same time, mysteries invite humility. They remind us that human reason, powerful though it is, does not command the whole of reality. Our models and equations reach far, but not infinitely. Our instruments peer deep, but not without end. At the frontiers, we confront questions that may always exceed our grasp. And in that confrontation, we glimpse the paradox of knowledge, that to know is also to know what we cannot know. Perhaps that is the essence of the final mysteries. They are not puzzles to be solved and set aside, but horizons that remind us of our place. To live with them is to live with awe, with wonder, and with the recognition that existence is greater than comprehension. We are finite beings in an infinite-seeming cosmos, conscious minds in a universe whose origins and ends remain obscure. The final mysteries are not obstacles to knowledge, but its deepest expression, that reality always surpasses us, and that our quest, no matter how far it reaches, will always find new horizons. Chapter 10. Embracing the Unknown. Throughout the history of science, the unknown has often been regarded as an obstacle, a barrier to be broken, a void to be filled, a shadow awaiting illumination. From the earliest natural philosophers to the most advanced physicists of today, the central motivation has been to transform mystery into knowledge. Yet as the scope of inquiry has grown, a parallel realization has taken root. The unknown is not merely a temporary absence of facts, but a permanent and even necessary feature of human understanding. The more we learn, the more we discover new layers of uncertainty. To embrace the unknown is therefore not to surrender in defeat, but to recognize that limits are woven into the very fabric of knowledge. This recognition emerges from many directions. In physics, the structure of quantum mechanics places unavoidable constraints on what can be known. The uncertainty principle ensures that precise measurement of complementary variables is impossible. In cosmology, the finite speed of light and the accelerating expansion of space create horizons beyond which no observation can ever reach. In logic, Gödel's incompleteness theorems demonstrate that mathematics itself contains true statements that cannot be proven. In neuroscience, the brain faces its own boundaries of perception, memory, and introspection. Each field reveals not only knowledge, but also the contours of ignorance. And yet, science continues to flourish. Rather than collapsing under these limits, it adapts. In quantum physics, researchers shifted from seeking deterministic trajectories to developing probabilistic descriptions that yield unparalleled predictive accuracy. In cosmology, horizons do not end inquiry, but focus it, prompting indirect methods and creative theories about the early universe. In mathematics, incompleteness does not paralyze the field, but inspires new axioms, new logics, and deeper insights. The boundaries of knowledge are not absolute walls, but horizons, against which science leans and from which it derives direction. To embrace the unknown scientifically is to understand that every answer generates further questions. When the structure of DNA was revealed, it solved the mystery of genetic inheritance, but opened vast new fields of molecular biology. When the cosmic microwave background was discovered, it confirmed the Big Bang theory, but raised new puzzles about inflation and dark energy. Progress is not a march toward finality, but a recursive unfolding, where each layer of understanding reveals deeper layers of ignorance. In this sense, ignorance is not the opposite of knowledge, but its companion. This interplay between knowledge and ignorance reshapes how science is practiced. The framing of research questions depends on recognizing what is unknown. Experiments are designed not to confirm what we already know, but to probe where knowledge runs thin. Hypotheses thrive at the boundary of the unexplored. Even the scientific method itself is built on the acknowledgement of uncertainty, requiring results to be testable, falsifiable, and open to revision. Science does not erase the unknown. It thrives on it. The embrace of the unknown is also visible in the philosophy of probability and statistics. Classical physics imagined a world of exact trajectories, but modern science frequently deals in probabilities, error margins, and confidence intervals. This is not a sign of weakness, but a recognition of reality. No measurement is exact. No model is free of assumptions. The quantification of uncertainty is a way of making the unknown explicit and usable. In weather forecasting, medicine, and finance alike, probabilities guide action in the face of unpredictability. Knowledge is expressed not as certainty, but as structured uncertainty. Complexity science reinforces this perspective. In nonlinear systems, even when the rules are known, prediction may be impossible beyond a certain horizon. The weather cannot be forecast in detail months in advance, but climate patterns can be modeled statistically. Epidemics cannot be predicted case by case, but their spread can be understood in terms of probabilities and thresholds. Here, embracing the unknown means acknowledging unpredictability while still extracting patterns and tendencies. Knowledge is reframed as insight into possibility rather than exact foresight. The same is true in neuroscience. The brain is not a flawless instrument of truth, but a biological system evolved for efficiency, not accuracy. Its memories are reconstructed, its perceptions filtered, its reasoning biased. To embrace this unknown is to recognize the fallibility of human cognition and to compensate with external aids: writing, computation, collaboration. Science itself can be seen as a collective extension of limited individual minds, pooling observations and correcting errors across communities and generations. The unknown, at the level of the individual, becomes manageable through collective inquiry. Artificial intelligence adds another layer. Machines simulate knowledge in ways that are sometimes indistinguishable from human reasoning. Yet their understanding remains ambiguous. They generate answers without consciousness, patterns without intentionality. Embracing the unknown here means acknowledging the gap between simulation and comprehension, while still harnessing AI's capacity to augment human inquiry. Machines extend our reach, but they do not remove the boundary between information and meaning. That boundary remains one of the unknowns, reflecting our incomplete grasp of what it means to know. Perhaps the deepest embrace of the unknown occurs in confronting final mysteries: why the universe exists, why it has the laws it does, why consciousness arises. These are questions for which science offers partial insights but no complete answers. Some may remain forever beyond reach, not because of insufficient data, but because of the nature of reality itself. The recognition of such mysteries is not an admission of failure, but an acknowledgement of the scale of the cosmos relative to the human mind. To embrace them is to accept that knowledge has limits, but meaning persists within those limits. The role of humility cannot be overstated. Scientific hubris, the belief that all will be known, has been tempered by discoveries that highlight boundaries. The universe is not a clockwork mechanism unfolding predictably, but a dynamic system with irreducible uncertainties. Logic is not a perfect mirror of truth, but a framework with gaps. Human cognition is not limitless reason, but finite perception. Embracing the unknown is thus a practice of humility, balancing ambition with recognition of limits. This humility does not diminish science, it enriches it. By acknowledging the unknown, we frame our questions more carefully, test our assumptions more rigorously, and interpret our models with greater nuance. The unknown becomes not an absence, but a guide. It shapes the direction of inquiry, pointing to where the most profound discoveries may lie. It preserves the sense of wonder that drives curiosity. At an existential level, the unknown is also part of what makes human life meaningful. If everything were predictable, If all mysteries were solved, the universe would lose its depth. Surprise, discovery, and wonder would vanish. The unknown sustains imagination, fuels art, and inspires philosophy. It gives us a reason to look upward at the night sky and inward at the workings of the mind. To embrace the unknown is therefore to embrace the essence of being human. Finite creatures in an infinite-seeming world, limited yet always reaching. In the end, the unknown is not a shadow to be feared, but a horizon to be acknowledged. It reminds us that our maps are partial, our models provisional, our instruments finite. Yet it also assures us that there will always be more to learn, more to explore, more to imagine. To live with the unknown is not to surrender, but to participate in a cosmos that is larger than ourselves, a reality that forever exceeds comprehension. And perhaps this is the final reflection, that embracing the unknown is not only the destiny of science, but the condition of existence. We live surrounded by mysteries, bounded by limits, yet carried forward by curiosity. The unknown is not a void to be conquered, but the ocean in which we swim. To embrace it is to accept that the quest for knowledge has no end, and that in this endlessness lies its beauty. And so, my friend, we come to the end of our quiet journey through the boundaries of knowledge. If you're still awake and wish to wander further, another video awaits you with more cosmic reflections to guide you deeper into rest. But if your eyes are already heavy, then let them close. May your dreams carry you softly among the stars. Until we meet again,